Thank you very much, and welcome to this DPG meeting. And it's a great pleasure and honor for me to introduce the next awardee. And the next award is given to Professor Rainer Blatt, centered at the University of Innsbruck. And the award we're going to celebrate in this talk is the Herbert-Walther-Prize. And the Herbert-Walther-Prize is giving out for outstanding contributions to quantum optics and quantum information science in this year to Rainer Blatt. And just let me use a few moments to introduce Rainer Blatt to you. Rainer has, if you look at his CV, he has about 17 scientific career steps, many of them in parallel. He has 28 awards he can look back to, including this one, and I'm not gonna waste your time and Rainer's time by telling all of them, but please allow me to give a few steps of his career. Rainer started out his work at the University of Mainz, and then he moved on to work as a postdoc at Chile in Boulder, and they're working with Chen Hall, who in 2005 received the Nobel Prize in Physics. Then he went back to Germany, and the next major step was that he was working at the University of Hamburg together with Peter Toszek, and starting there his own activities centered around or continuing his work on trapped ions. Then from the University of Hamburg, he moved on to become a chair of experimental physics at the University of Innsbruck, and this was in 1995. And then in 2003, became a member of the Austrian Academy of Sciences and co-founder of the Austrian Academy of Sciences Institute on Quantum Optics and Quantum Information. From his additional awards, I only want to name a few of them, and there's one I would like to mention, which is the Schrödinger Prize of the Austrian Academy of Sciences in 2005 or 2006. Then we have the 2009 Carl Zeiss Research Prize. In 2012 we have the Stern-Gerlach Medal, so he's also a distinguished member of the Club of Stern-Gerlach, medal winners of the German Physical Society. 2021 he was, 2019 I should say, he was an international member of the Academy of Sciences of the United States. 2021 of the European Academy of Science and Arts, and in 2003 also he got a member of the German Academy of Sciences, the Leopoldina. Rainer is famous, and he's at the heart of what I would call, and what everybody often recognizes now as the second quantum revolution, with his work on precision spectroscopy, quantum metrology, and quantum information science with trapped ions. Since 30 years, he's the leading person, one of the leading persons in that field, and he's, as I said, centered at the University of Innsbruck, but also at Munich, at the Max Planck Institute of Quantum Optics, at the Academy of Sciences in Austria, and is the scientific director of the Munich Quantum Valley. So he's distributed over many entities, but he's here today, and we're looking forward to your talk. Welcome, Rainer, and congratulations to this year's Herbert-Walther-Prize.
Thank you, Gerhard. Thank you for this lengthy introduction. You should have shortened it because you took away at least 2 minutes of my talk. Okay. Thank you for being here with me today. It's a pleasure to see so many people after the COVID times, and it's a real pleasure to share this stuff with you. What I'm going to talk about to you today is sort of results of the last 10 years. What you see here is quantum computation, quantum simulation, and strings of trapped ions, which are confined in a trap, as you can see here. And I dedicate this talk to Herbert-Walther, who passed away way too early, and who was one of the pioneers in quantum optics in Germany, and also was one of the pioneers with ion traps, besides Peter Toschek and a few others, but he also had a very strong group at the Max Planck Institute there for quantum optics. So let's see what the menu is of today's talk. I would love to briefly talk about, I have to get away from the loudspeaker here, otherwise we will see first why and how we are actually using trapped calcium ions for quantum information processing. I will briefly tell you what the toolbox operations are that we employ, and just give you a few characteristics of our workhorse, the Innsbruck quantum computer, and then just give you a few examples of quantum computation. It's mostly simulations and measurements, and if there's time enough, we'll discuss how we possibly can scale this up. Of course, there's many sponsors who have contributed to this and still contribute to it. The work has been carried out at the University of Innsbruck, of course, in conjunction with the Institute of Quantum Optics and Quantum Information of the Austrian Academy of Sciences. So let's begin. This is the workhorse as we usually see it, as a sketch, but it really looks pretty much as the trap as you've seen in the first slide. It holds in the center a string of trapped ions, and of course it's illuminated by laser light in order to cool them, to manipulate them with these addressed beams right here, and we can see the fluorescence light with the CCD camera. Typically we get strings of about 50 ions like this. It's not a typical string that is typically the best that you ever observe. This is really something we work with every day. So this is a typical string that we have as a register for our quantum computer. What are these ions? These ions are calcium plus ions, as you can see here. In the level scheme, we have the qubit encoded in this metastable transition level D5 down to the S1 level. The lifetime is about 1 second right here. And we detect it by measuring it with a dipole allowed transition on the P1/2 state right here. This scatters a lot of light once the system is down there. Once it's projected, of course, there, it doesn't scatter because the electron is not available. And that gives us a very close to 100% quantum efficiency for detecting where the state is. For all practical purposes later, we denote, of course, the spin down state. That's the bright one. The spin up state is the dark one, or logical 0, and this is the logical 1. Of course, this is tantamount to saying this is a sigma C measurement. And of course, it allows you to see these proverbial quantum jumps that we have seen already for the first time in Hamburg in '86 in Peter Toschek's group. So this is the outset. So let's get started. Remember, we have a two-level system sitting in a harmonic trap. And of course, we have to diagonalize that particular Hamiltonian in such a way that we have many two-level systems sitting side by side, which are just different by the trap frequency nu. So we denote this with the levels n of the phonon numbers, that's the harmonic oscillator right here, and the electronic level ground state or excited state. This allows us to give very many resonances like in a vibrating molecule. If we detune the lasers such that it's on-resonant, then we just affect the internal degree of freedom only. But if you detune it, say, to the lower sideband, as we say, we excite one phonon less of the system, which of course then gets scattered away because it predominantly scatters here and climbs down the ladder until it resides in the ground state. So this is what we call ground state cooling. It's just optical pumping of the vibrational states. And in this case, we are left with exactly 3 transitions, which is just the blue sideband, adding a phonon, and the red sideband, taking a phonon out of this. In other words, the carrier, that's the on-resonance transition right here, is used to manipulate the qubit. This is the internal superposition, and the sidebands are used to create spin-motion entanglement, or the entanglement between the motion and the qubit. And this was then proposed to use for a quantum computer by these people, Ignacy Sirac and Peter Zoller, in this famous paper 95. You find more of these things here, but remember, what you need in order to create the entanglement as a system is the internal degree of freedom, of course, coupled to the motion in the trap. Now, we of course use now many of these things. We have a collective way of seeing these ions. We can just shine in a laser along the axis, seeing all of the ions simultaneously. So this is what we call a collective local operation. It goes with a high fidelity and very short times. And we have individual local operations, so we can just point, as you saw on the first slide, a laser to one of these individually trapped ions right here, and we usually do this off-resonantly. That causes a stark shift and the phase shift accordingly, and that's one of the gate operations that we are using. The entangling gate operation is there in order to create the superposition of, say, two adjacent particles at the same time. Entanglement is a superposition of, say, qubits stored remotely in Hilbert space. That's done, in this case, with a bichromatic excitation. We call this a Milmer-Sørensen gate. By bichromatically exciting these things, you all know that in two-photon transitions, if you apply them right, of course, the two-photon transition is first-order Doppler free. And the reason for that is simply that you have these pathways which are just going through these various phonon states and immediately excited. And of course, if you close the path right here, then they just add and cancel. And this is what we are using here to our favor to do the entanglement. It can be shown, and was already shown more than 15 years ago, that these three blocks already combined give a universal gate set for arbitrary quantum computation. Of course, nowadays we are just using then a few more of these gate operations, but just to summarize the basic gate operations for the more mathematically inclined. This is the stark shifts, this is the unitary operation. It's usually denoted as a box operator pointing out a single operation right here, or the box talking to all of these qubits. The lines are the qubits, and this is time going to the right. So this would be a collective stark shift by applying a detuned laser to all of them simultaneously. This would be a collective stark shift, but just generalizing now the phase to that superposition, you can just do this also with a combination of sigma x and sigma y to add to the sigma phi right here. And of course, the entangling operation can be written as a spin-spin interaction in this way of writing this. This is the entangling operation that you saw due to two-photon transition. In the meantime, we have many more of these operations and use them as a toolbox. This is the hiding operation, so we can just optically just pump or just hide them in an excited state, so they are not participating in any operations that we apply to the rest of the register. Or we have dephasing operations. We can just use this for open systems. We have initialization reset operations, typical optical pumping operations, and we have even the possibility to create a quantum cache memory, saying that for, say, a certain amount of time, we can even hide a full quantum bit with all the coherences in some stable states that are not affected by the operation of the quantum computer. And then we just do this. So this is a myriad of things, and this requires some compilation. I don't have that time to talk about that today. But whenever I just talk about these operations later in algorithms, of course, the underlying part is that we have an optimizing compiler doing all these things. So the situation looks then the following. We start with a superposition, have a quantum processor, which is broken down in a sequence of these operations, these gate operations, and we end up with a superposition right here. In the end, you get classical information. The classical information really means you have to project the system, and you get it down there. And of course, you have to repeat this, because after all, this is a statistical way of describing these things. But that, if you do the proper, this in the proper way, you don't have to do that many times, maybe 5, 10 times to see the distribution right here. Okay, now let's go to the lab. This is how a typical lab looks like. I don't have to tell you that. You all know this. So this is lasers, this is optical tables, all the stuff, and this is where the students are sitting at and just doing all the work. The ions are hidden here. The rest is just lasers and a lot of infrastructure. And of course, then you can just do whatever you want. And all of these algorithms have been done in the lab over the last 10, 15 years. And I don't want to delve into the details. I just want to mention now that we were sort of fed up with all this hassle in the lab. And we thought about creating a smaller device. In 19-inch racks that you can have an industry standard that you can even sell later on. And this is the typical optical rack that we have. We have a trap rack like this. And over the last years, we developed this in the, within the action cooperation, which is a flagship consortium by Christian Marciniak and Ivan Bogorilov. They were in charge of that. And this is how it looks like. This is the consortium that contributed to it. And so you see here the laser rack, and this is the trap rack. And I'll come back to these things a little later. So this is now the workhorse that we have in Innsbruck available, and we can use it routinely. Just from the outside, you just close the doors and just program things. And we have, in addition to that, to these manipulations right here. We have addressed manipulations that we can do simultaneously. And we have added even here the possibility to do an addressed member-Sørensen gate operation. Just to give you a few features. The T1 time, according to what we have, really is approximately 1 second, defined by the lifetime of the excited state. The T2 time measured is really roughly about half a second, as it should be. We work routinely with 20 plus, between 20 and 50 ions. We can load to 100 ions, but we typically work at this time with 20 to 50 ions. We demonstrated already 24 qubit GHZ state, and it supports KISS, KIT, circ, whatever you like. This system is available on the cloud, so if you want to get access to that, talk to us. We can give you access to this, you can do your calculations on it. Just to give you an idea, we have an automatic tune-up. We have single qubit control, of course, single setting of member-Sørensen up to 20 qubits automatically, and with full connectivity. This calibration is sped up, of course, with this automation. And this, to give you an idea, tunes up to a fidelity of about 99% in 30 seconds. That's the boot up procedure. You push a button, and half a minute later, you can start the measurement. I can tell you, this is not my doing. This is the doing of many students of the teams. And I can tell you, this is a lot of work, but they have done it. And they are to be congratulated on that. So let's just see just a few examples. This is the 50 ion chain, typically addressed. We can do possibly more, but then of course there's some work to be done on the outsides here because we are losing power. But 50 is, this is the 50 qubit matrix addressing. These are all numbers, you're not supposed to read them. The nearest neighbor crosstalk is about 1%, 1.2% right here. The average crosstalk is a lot less. We can do something which we call addressing error correction, which is just using concatenated pulse schemes, which you might know from NMR and from other pulse schemes, that allow us to minimize these things. So we just have typically average crosstalks of about 0.2%, which is generally correctable. We have off-resonant errors when we just use the Stark shifts, which are really completely negligible at 10 to minus 8 error rate. So this is fine for all practical purposes. And the 2 qubit gate performance is slightly worse, but still okay. So we have now member-Sørensen gates. We just apply a number of member-Sørensen gates, in this case, to all 12 ions in this case. This is one of the measurements in the automatic tune-up routines. The fidelity of this comes out to be 99%. If you just do this at this time, this works. If you want to get more than 99.5, 99.8%, which we can do, you have to employ a postdoc or maybe another PhD student to really work hard on it. This doesn't work automatically. So there's still room for you to work in the lab. Here's the limitations. We have to make the member-Sørensen phase shifts. Of course, when you do a member-Sørensen gate, there might be some other ions which are not participating in the ongoing gate operation. We call them spectator ions. These spectator ions sometimes suffer from the phase shifts, and we can control them because we can correct for them, we can calibrate that. It's usually correctable. Unfortunately, we have some dephasing on these spectator ions as well. And this is not just a shift, but it's different phase shifts, which we cannot avoid to all of them. And that adds to an error which is slightly bigger than the threshold that we eventually need for quantum error correction. So this is where we are at this time, but we need to go an order of magnitude better. So this is currently the culprit when we are talking about quantum error correction. I'll come back to that in the end. So this is not where we are yet. Okay, so that's the status quo. And in the automatic tune-up routines is one routine that allows us to simply generate, say, a GHZ state. A GHZ state is all ions up and all ions down, the superposition of them. It's one of the most sensitive states that you can produce, so it's tested whether that survives what's the coherence of the system, because that gives us then a hint on whether the system is stable enough to be used for carrying out calculations. And you see the so-called entanglement width is about 50% of this GHZ fidelity. We can claim we have 24 qubits that are really entangled, so this is 24 qubit entanglement, and that works. So we routinely claim more than 20 entangled qubits. We might have even 50 entangled qubits. Unfortunately, we cannot prove it. And of course, we are talking to people, theorists, to allow for more witnesses, for more tests. This is the simplest test that we can do, and that's where we are currently. Okay, so let me just come to a few applications here. The applications that we mostly do at this time are computations. I'll come back to that, but I can summarize them also under the possibility of simulations. A quantum simulation is essentially an approach where you try to simulate something that you cannot really do on another machine, and you try to use a quantum computer in this case in order to do that. So for example, suppose you had a spin system right here that you describe with the Hamiltonian. That's forbiddingly difficult on a classical computer. Then you go to a quantum computer, say for instance on Einstein, or say an atomic lattice with Pascal, or say go to a Manuel Bloch lattice and things like this, or even the superconducting quantum computer. Then you have essentially 3 different procedures which are there for quantum simulations. What are these? The first one is what I call an analog quantum simulation. In an analog quantum simulation, you just study your system, you look at the interactions that you have available, and once your system allows a certain match between the engineerable interactions and the model that's to be simulated, then you can just create a Hamiltonian, and from that the unitary operation that you require in order to see the dynamic evolution of the system. So you apply this for a certain amount of time, which of course the analog part of the implementing this. This is what we call an emulation. And then you stop the system and measure and see how the the behavior is of the system. This is what we call the analog simulation, because since it's in an analog fashion emulating the behavior of the system, and you cannot really control this to the extent that you do error correction in each step. The more computation part is this digital simulation. Here you break down everything, as said before, in a sequence of gate operations like the unitaries that I said before. And this is done in a completely programmable way. And of course it requires very many of these operations. And then of course, in principle, after each correction, after each operation, you could make a correction. You could make error correction. So this is what you really want to have for a full-blown quantum computer in the end. But for many of the quantum computers that we have today, it is exceedingly difficult, and we have really errors in the system that are not controlled. So this works for small systems and for more small problems, but this is probably the one that breaks even earlier than that. And there's a third part here that's heavily used these days by very many people, what we call a hybrid simulation. So the problem then is cast in such a language that it lives in a classical computer. So you store your Hamiltonian, for example, and you're capable of calculating expectation values from certain parameters that you have. Then a computer comes up, say, with a certain parameters set, thetas, that's a vector of maybe, say, 10, 15, 20, or even 100 values that you have. And then you say, okay, I'll tap into my Hilbert space, of in this case, an analog quantum simulator, or more generally, just a quantum register. This allows you, because you're addressing things, to reach every nook and cranny in your Hilbert space, if you want so. And then you just don't do the calculation in this quantum register, but you just measure this register and feed back one value, in this case the expectation value. And then the system decides, does that agree with what I have expected? And if it doesn't, it just goes on, and finally, in an iterative process, it determines these things. This is also heavily applied. I'll show you some examples. Just to give you an example, this for the digital approach. Again, we have all the unitaries. And if you had then the Hamiltonian to be implemented, you find very often that these don't commute with each other, but you still have to then come up with a unitary that does that. In this case, you just can go down to what we call the Trotter-Suzuki approximation. That means you just employ the piecewise Hamiltonians right here. Each piece for a certain amount of time, of course, you can implement in this way by unitary, and then you cut it in slices, and you repeat these sequences n times. And it's shown by Trotter and Suzuki that this, of course, then really approximates the entire dynamic behavior if you have fine enough slices. And if you want to know more, I refer to some reviews. This can be done in an analog approach in a different way. In the analog approach, for example, just to give you an example here, we apply, for instance, the bichromatic radiation from the side. The bichromatic radiation, you remember from the translation table, is a spin-spin interaction. And also, I can detune the system from the center frequency right here, but the tuning amounts to having, say, a Stark shift. And all put together, you see immediately, that looks pretty much like a Hamiltonian. I know, this is the famous Ising model, describing the behavior of spin systems. Now, if you just apply that for a certain amount of time, then you see the dynamical evolution in your spin chain, and you can stop the system and just measure this. This is what can be done, and the JIJs can be adjusted according to trap parameters. There's a nice review by our colleague Chris Monroe at the Duke University, and if you want to know more about this. This is, for example, an example that we measured many years ago in digital simulation with a 4-spin system, for example. And then you see, of course, the theory curves are the lines here. The experimental values that we expect here are the open squares. They don't match the experimental values. The reason for that is simply that we do not correct for errors that appear in each gate operation. There are very many gate operations, and you run slowly out of steam. So this works to a certain extent, but not for, if the system becomes too complicated, then you run out of problems, run into problems. We applied this also to what's a more interesting physics problem right here. This is the so-called 1D lattice gauge theory. It's a Schwinger model, like a simplest case that you can do for quantum electrodynamics. And this is cast now in a, what we call a Pauli form. Details don't really matter, but you can just do this, so you just get the long-range term, you get a hopping term, and they get the mass terms. And make a long story short, you can recast this, of course, in the so-called Trotter-Suzuki sequence. This gets repeated many times, so it's about 220 gate operations that you apply. But you can actually see that you really can recreate here the so-called pair-anti-pair creation in the system, and it matches the theory very well. Analog simulations here by the team of Chris Monroe, for example, they have done some phase transitions that they observed just by seeing the parametric to ferromagnetic crossover and the Néel ordering right here. We have done the similar things by seeing transport phenomena. You create entanglement in this case. All of these Hamiltonians have been done. We have studied extensively over the last 6, 7 years transport phenomena. For example, you just have here just a ballistic transport, as in this case. You just have create one excitation that just under the interaction of, say, the Ising Hamiltonian, it just spreads out. But then you can create also, for example, disorder. If you have disorder in the system, that transport is hindered, that you have get Anderson localization. But now you can just say, okay, now my disorder has some noise on it. If I just shake the noise a little bit, then of course this localization gets weakened and the system gets sort of a diffusive transport again. And if you now shake very hardly here, then of course you remeasure the system, you get a quantum Zeno effect, so the diffusion gets over there. In fact, we can even study, say, hydrodynamic behavior, Levy flights in the entire system. All of these things can be simulated. And finally, an example on the variational quantum simulations right here. This is what I told you, is take the system, break it down into the sequences right here, to have the Hamiltonian in the quantum computer and tap into the Hilbert space provided by the register here. This is just one iteration run, for example. You see here the energy that is measured, that's the expectation value that we measure and calculate here with the computer as a function of the iteration number. This looks like a Fleischert plot, and the reason is simply because you don't want to get stuck in a local minimum with so many parameters. This is about 15 parameters here. Then you just have to add a stochastic component to make sure that the system doesn't get stuck somewhere. And you see here, this goes nicely down. This is a Bayesian estimate of the energy. Question is only, where do I stop? Usually you have to stop at some resources because you never can prove that I'm at the absolute minimum, except for the fact that you can actually iteratively determine the error bars also from the variances. And remember, when you just take the variance right here and you can just measure that in a similar way, then, you know, once you've found an eigenstate, this variance should vanish. So if that's small enough, you can prove in a self-verifying way that the system actually has found an eigenstate. So these things are all doable. They take time, but they're manageable. And this has also been applied to quantum chemistry calculations. We have done this for the hydrogen here, for lithium hydride. The group of Chris Monroe has done it for water molecules. You see all these molecular curves can be calculated. I remind you, that's nice, but it's all toy problems. Real world problems, beating classical computers, is still far off. I'll come back to that in the end, because that's really not yet where we are. But we're on the way, and the potential is at least visible. Let me conclude here with one more measurement that we did last year, showing you how we can even optimize metrology with these variational quantum circuits. This is work done experimentally in our group by Christian and Thomas Feldker right here, and of course the theory work was guided by Peter Zoller and his PhDs in Raphael Kaubrücker. What do I mean with this? This is the proverbial optical clock that we have anyway. So we just have a two-level system like the qubit that we have here. What you want to do is, for an optical frequency standard, you want to know the frequency very precisely. And of course, what you do, we've done that a long time ago, you just make a Ramsey experiment, a pi/2 pulse, wait a certain amount of time, another pi/2 pulse, it goes up or down, depending on the tuning, and you see this is the nice features. And we can do this even better, say this is a 50 hertz or 20 hertz line. Let's see right here, you see these things can be done. And the current, because we do this side by side with our measurements anyway, the current value of this frequency is this value measured by Milena just last year. And this is also nice to know for BIPM, and it's a secondary frequency standard. So this is what we have. Now the question is, when we do measure this on a single ion, of course, that's what we can do. But can we improve on that with quantum technologies? So let's have a linear ion trap, and let's say, okay, I'll do this with 10 ions or maybe even 100 ions. Then I have the following leeway. I can just replace this simple unitary operation, the simple pi/2 pulse, by say a more general unitary operation, and in principle the decoding pulse, or say the what I take the measurement pulse right here, could be generalized to a decoding pulse like that. And then of course we measure the excitation, and then we ask ourselves, can I improve on these local and the entangling operations that I have here? Can I just optimize these parameters in a variational ansatz? And then let the system go and iterate it and see whether I can find an optimal. What do I optimize? Now we want to estimate the interferometer phase, because that's a Ramsey interferometer, same thing for the atomic interferometry, or for a two-level system when you just do measurements. We calculate the mean squared error, make a Bayesian estimate from a prior distribution, and then we just know what the imprecision of the variance is and optimize these parameters accordingly. So the cost function that you define in this way, of course, is important. Once you have defined this very well, then you can just go and turn the system on. When we do so, we find the following. If for a simple Ramsey sequence, we find the sine curve. Remember, the Ramsey sequence usually is pi/2, pi/2. Okay, that would give you a cosine curve, but if you just change the phase in between pi/1 and the second pi/2 pulse, you get a sine curve. And this is for the interferometers right here. So you want to stabilize the interferometer there. So now you just take a quantum projection noise and you see, okay, what do I expect from the mean squared error that I just get here? To get a curve like that, that would be the prior distribution if you take that in the Bayesian sense. So these numbers are simply to say, okay, we have nothing done except for we just take as a simple Ramsey sequence. So we have a classical coherent spin state, standard Ramsey, and a classical pi/2 pulse for the detection. Now when we take first the Mellmer-Sørensen gate operation right here, remember the Mellmer-Sørensen gate operation was a spin-spin interaction, or in terms of atomic interferometry, it is sometimes called it's a one-axis twisting operation. So you just squish the system and twist the system on the Bloch sphere. Then you get a squeezed spin state, and that squeezed spin state doesn't change very much the total spin detection that you get here, but it changes, of course, the errors, because you get reduced errors right here. As you expect from a squeezed spin state, you see it's sort of a sharpening of the distribution on the Bloch sphere. But now the next point is I can just change the tailored measurement. I don't use a simple pi/2 pulse, I make a tailored measurement. And why do I improve now my system? I improve my system because the catching range of the interferometer gets bigger. This is very linear right here. It gets, the slope gets a little less, but that doesn't really matter. It's only a matter of the signal-to-noise ratio. And also, I'm getting a little less noise in the center, but it's not perfect. But if I do things now twice, both the tailored and input and the measurement, then I get a behavior which is definitely better in a wide range and has a lot less noise. So I can just optimize my measurements. On the spin picture, if you have the Teuton spin checker and the Bloch sphere, you just have a banana shape, and you're just adapting sort of the tailored measurement according to that banana shape to get the optimum behavior here. And here is just a summary on this. The optimum quantum is just the red line right here, and we are very close to that. We expect these things to be, they can't get better than that, but this is what we get, very close to the optimum quantum way. So we get an improvement of several dB for only, say, 10 particles that we have here, and 16 particles in this case. You could easily just do this with 100 particles, and then you can actually improve every system already by using these quantum technologies. With this, how much time do I still have?
-5.
-5? I'm sorry for that. Okay, so then -5 minutes is fine. So let's just talk about the scalability goals.
You're the guest of honor.
Meaning?
At your mercy.
Thank you. No, I don't want to spoil the stuff for these two guys who come after me here. So let me summarize here. I will just summarize a few things which I find important and should be important to you as well. What are the strategies for scalability? What can we do and where do we go? Now, we want to need more. Scalability really is it's about more things. We need more qubits, so we need better traps. Sometimes we want to go to two-dimensional traps against arrays of things. But we want also to have more operations, better control. That requires quantum error correction. I haven't been able to talk about that one. We need more computational power, so we need quantum software solving a key problem. This is not solved, this is an open problem. And we need what I call predictability. The reason for that is the following. We know, of course, how the components behave, that is to say a single qubit operation, a two-qubit operation, and a single system. But if you really want to scale the system up, can you predict from the behavior of a single transistor how a computer with a myriad of transistors behaves? Electronically, this is pretty well done. In a quantum system, you cannot. And you find this out when you just compare the various systems that are available. And this is something that we really need to work on. Second thing is we need scale down. We've shown you how we can miniaturize the control hardware. We can go from an optical lab to 219-inch racks. But we need also less errors. So we need to protect our system in a passive way, what we do anyway. But we need also go to quantum error correction in an active way. And we need a lot more faster gate operations as we have at this time. And something that's usually not considered, what I call scaling out, we need interconnectivity. Interconnectivity means we need a modular design, optical interfaces hardware, and quantum parallel software. This is a task that goes way beyond the mere just scaling up the hardware than we have here. I could go on, I don't want to ramble on with this. I could just talk a little bit more about quantum error correction. We don't have the time. But if you want to talk to me in more detail, let's do this. Let me just, rather than that, come to the dream and the vision that is in all this. What we really want in the future is a quantum computer that is comprised of logical qubits. A logical qubit is a qubit that consists of, say, encoded physical qubits. So you just have one qubit hidden in, say, a number n, 7, 17, 20, 40, whatever, physical qubits that allow you to correct for errors that appear during the operation of the system. And then, of course, you protect them by error correction, and you interconnect them by dipole-dipole interaction on chip or by ion cavity interfaces. This is just the artist's rendition 5. Typically, we are using now already groups of 10 in order to do that. And in future, we may even need 20 or 50. There was last week a very nice paper, if you want to look at it, by the Google team. They had about 49 of them, and they studied the behavior. That shows you rather more where the system will go in the future. Where do we go? We have more qubits, of course. We can go to 100 if you want with the same technique, but we need better fidelities. We need faster gate operations, faster detections, and we already are developing 2D trap arrays onboard, addressing onboard electronics. But this is still an open question. How can we actually characterize a system? How do we know what entanglement do we have? The amount of entanglement in the system, if the system is really big. This is an open question. And for me, the holy grail is to keep the qubit alive. This is what we are addressing in the so-called equal project. And once you have that, then all of this gets much better. The task is not done, but this is something that you can do once you have all of these things available. This, of course, was not done by me. This was done by a large team. This is the team of last year. Of course, this would not work without the help and the cooperation with many theorists, among them, of course, predominantly Peter Zoller and his team, and Markus Müller, and many others that you can see here. These are the names. They don't tell you very much, but they tell me very much. And I would like to thank all of the current members and the former members of the team. That prize is a prize for you too. Thank you all for coming, for listening to me. Thank you for being with me. And then you see here this is the nice place where we are. We can make it. We made it in Tyrol. And this is now the commercial system that's available. If you want to talk to Thomas, you can buy it. And this is proudly made in the Tyrol. Thank you very much.
Thank you.